Welcome back to the deep dive. Today we're tearing down one of the most fundamental and frankly most confusing debates in the world of large language models. Where do advanced reasoning capabilities actually come from?
Yeah, that's the big one. It's the question that keeps researchers up at night. I mean, we have these incredibly powerful models now, right? They're capable of complex logic, problem solving. But when a model gets smart, how much of that genius was baked in during that massive multi-trillion token pre-training phase? And how much was actually taught later during reinforcement learning or RL?
That is the core conflict in the literature right now. You read one paper that argues RL is just a glorified editor. It sharpens the text, aligns the output, but doesn't actually give the model any new math skills or logical abilities. Then you see other evidence suggesting models gain substantial, genuine reasoning capabilities post-training. It's wildly conflicting.
And the reason for this fundamental disagreement is, well, it's the opacity of the modern training pipeline. You are training models on vast, largely unknown slices of the internet. You have absolutely no idea which specific logical rules or reasoning primitives the base model has already swallowed and internalized. This lack of control means we can't perform causal attribution.
Right.
If the model solves a hard problem after RL, did RL teach it? Or was the answer just hiding in some obscure corner of the 10 trillion token corpus?
So we've basically been trying to reverse engineer a black box, hoping to see what's inside. But the box is just too big and too dark.
Exactly, and the process has gotten even more complicated with the growing popularity of an intermediate stage, mid-training. Sometimes it's called continued pre-training. This stage uses higher quality instruction-formatted data to sort of bridge the gap between that chaotic general pre-training and this structured reward-based RL. It acts as an intermediate distributional bridge. You see it in successful architectures like Quen and Alama. If you don't understand what that stage contributes, figuring out RL's true impact is just guesswork.
Which brings us to our mission for today. We are looking at some groundbreaking research from Carnegie Mellon University's Language Technologies Institute. Their goal was simple, but I think really profound: escape the black box. They created a fully controlled experimental framework specifically designed to surgically isolate the causal contributions of pre-training, mid-training, and RL-based post-training.
They built a pristine white box instead of trying to understand a massive, murky black box.
Yeah,
It's the only way to establish true causality in this field.
Okay, let's unpack this. We're starting from the ground up to understand how AI learns to reason. So let's go back to that central ambiguity. Why is it so hard to isolate the effects of the post-training stages? Why couldn't prior analyses just use a very large, diverse, real-world data set and just assume the base model didn't know the answer?
The difficulty lies in the difference between absence of evidence and evidence of absence. When a model fails a specific complex reasoning task after pre-training on the general internet, we can't say for certain it lacks the capability. We can only say it failed to express it, or that the specific components needed to solve it were just too sparsely represented in the training data.
Right.
Prior analyses used uncontrolled environments, that massive unknown internet corpus. This meant researchers couldn't know precisely which atomic logical primitives the base model had already internalized.
So you might think you're testing the model's ability to combine addition and multiplication in a complex way, but in reality, some students' Reddit homework post from 2012 already contained that exact 15-step composition, and the model just memorized it.
Precisely. You can't separate rote memorization from genuine compositional reasoning. And that issue is compounded by mid-training. Mid-training is an essential but under-examined stage. It provides that structured supervision to align the model toward instruction following. If you run mid-training on high-quality code or math data, those gains might be incorrectly attributed to your final RL phase, further muddying the causal waters.
So the CMLTI team needed a completely clean slate, a sandbox, where they could control the environment down to the subatomic level. Let's get into the key innovation here, the controlled framework.
Their solution was to design the environment based on three unassailable principles of control and observability.
Okay, what was the first principle for achieving this granular control?
The first principle was using controllable synthetic reasoning tasks. They built their problems using the GSM Infinite framework. So instead of asking, a train leaves Chicago at noon, they constructed problems where the underlying logic is defined by a directed acyclic graph, or DAG.
Wait, can you simplify that for us? A DAG. What does defining reasoning by a DAG allow them to do?
Think of a standard high school word problem. It might say, John has 5 apples. Sarah gives him 3 more. If they split them equally with 2 other friends, how many does each person get? Would That process addition, so 5 plus 3, then division, 8 divided by 4, that is a graph.
Okay.
The variables, like apples and friends, are the nodes, and the operations, addition and division, are the directed edges showing the dependency. By generating problems based purely on these underlying computational graphs, they gain total control.
So they're controlling the DNA of the problem, not just the packaging.
Exactly. They can measure the exact complexity of any problem simply by counting the number of arithmetic operations, which they call op of G. If a problem has 10 operations, it's an op equals 10 problem. This gives them that precise difficulty knob you mentioned earlier. They can guarantee that the pre-training only sees op equals 10 and RL is later tested on op equals 20, ensuring genuine extrapolation.
That makes the scientific comparison possible. What was the second principle?
The second principle flows directly from that: observable, parsable processes. Because they define the ground truth as a specific DAG, the model's generated solution, its step-by-step reasoning trace, must also be parsable into a predicted graph. They call it G hat. If the model says, I'm going to add A and B, then multiply the result by C, that structure has to match the gold standard graph.
Wait a minute. So they are not just checking the final number, they are checking the recipe. If the recipe calls for A plus B and the model does A minus B, then even if the final result is accidentally correct, the model gives zero credit for that step.
Precisely. This is the cornerstone of reducing what they call reward or evaluation hacking. If the model skips a step or uses a convoluted illogical path but still arrives at the right numerical output, the process evaluation catches it immediately. They are evaluating reasoning fidelity, not just predictive luck.
And the third principle ties these components together across the training stages.
Yes. The third is systematic manipulation. Since they control the reasoning structure, the op of G, and the surface context like switching from a problem about lions in a zoo to students in a school, they can surgically adjust the data distribution across all three phases: pre-training, mid-training, and post-training. This ability to inject or remove specific primitives or complexity levels is what lets them establish those causal links.
Let's shift to defining success in this sandbox then. We're not just talking about simple accuracy here. You mentioned two key axes of generalization:
8.
depth and breadth.
Absolutely. The first is extrapolative generalization, or depth. This tests the model's capacity to handle problems that are structurally deeper or more compositionally complex than anything it was explicitly trained on. If it saw problems up to op equals 10, can it extrapolate those learned rules to solve op equals 20 problems? This is the definition of true capability extension.
So it's not just memorizing the answer to 5 plus 3, it's learning the concept of addition and applying it iteratively 20 times in a row.
Correct. And the second axis is contextual generalization, or breadth. This measures transferability. Can the model apply the same arithmetic skills, the same logical rules, across a completely novel surface context? If it masters the logic within the animal zoo narrative, can it immediately apply that exact same complex logic to the teacher school context, even if it has never seen complex problems framed that way before?
That feels highly relevant to real-world applications. When we use an LLM for highly specialized tasks, say reviewing a medical case, we need it to transfer its core reasoning ability from the general text it learned to the specific medical jargon it's now reading. It has to learn the logic, not just the narrative.
That's the test. And the evaluation protocol that underpins this entire study is the process-verified evaluation.
I want to spend a moment on this because it seems to be the highest hurdle for the models.
It is the defining feature. A solution is only marked as verified correct if two criteria are met simultaneously. The final answer is correct, and the intermediate reasoning steps, that predicted dependency graph, must perfectly match the gold standard process. They require what they call process accuracy equals 1.
Let me make sure I understand this clearly. So imagine a human student solving a long math problem. They make one tiny sign error early on, but miraculously that error cancels out later and they get the right final answer. Under traditional evaluation, they'd get full credit. Under this process-verified evaluation,
They fail. If the step-level logic, the process accuracy, is not 100%, the overall solution is marked incorrect. Missing nodes, dependency mismatches, or incorrect intermediate values all lead to failure. This is not just a hard metric, it's a standard of fidelity. It ensures the model is not relying on spurious correlations learned during training. It is faithfully executing the compositional logic.
that raises a really important question. If prior research that claimed massive capability gains from RL only measured final answer accuracy, could those gains have been, well, vastly overstated? Could they have just been rewarding models for being lucky reward hackers?
That is exactly the point this paper implies. By enforcing process verification, they strip away the lucky guess factor. This rigorous metric, which they use for all reported PAS-OK scores, guarantees that when they see a capability gain, it's because the model genuinely learned the composition rules, not just the outcome distribution. For any mission-critical application, from code generation to financial modeling, this process fidelity is non-negotiable.
Okay, so we have our control environment and we have our hyper-strict evaluation standard. Now, we finally get to the core conflict. When does RL move beyond just polishing and start truly extending the model's reasoning competence? Here's where it gets really interesting.
This is the section that brings harmony to the conflicting literature. The researchers designed an experiment where they fixed the pre-training all models, saw tasks up to op equals 10 difficulty, and then they systematically varied the difficulty of the data used for the RL post-training phase.
Okay, walk us through the 3 difficulty categories they used relative to the base model's known capabilities.
They categorize the tasks into 3 bins. First, you have in distribution or ID tasks from op equals 2 to 10. These are things the base model had already mastered. Second, OD edge tasks. OD means out of distribution. These are from op equals 11 to 14, so just beyond what the model was trained on. But critically, the base model still has non-zero pass at 128 accuracy. It's failing its first few tries, but if you give it 128 attempts, so sampling 128 times, it occasionally gets the hard problem right.
That non-zero pass at 128 is the key. It means the capability is latent but not reliably expressed.
Precisely. It has the foundational knowledge, but hasn't perfected the deep compositional structure yet. The third category is OD hard tasks, from op equals 15 to 20. Here, the base model shows near zero pass at 128 accuracy. The problems are so far outside its training distribution that it basically fails every single time.
So they are testing. If we apply RL to tasks the model already knows, tasks it almost knows, or tasks it definitely doesn't know, where do we get the biggest lift?
And observation 1 is illuminating. Let's use a consistent analogy here. Think of pass at 1 as scoring a hole in one, getting it right on the first try. And think of pass at 128 as eventually getting the ball in the hole after many attempts. It's a measure of maximum possible capability.
That makes sense.
For the ID tasks, up 2 to 10, RL significantly increased pass at 1 accuracy. The model became much more reliable and confident on the first try, but there was virtually no improvement in pass at 128. This supports the capability refiner view. RL is excellent for sharpening and aligning existing skills, but it does not extend maximum capability if that capability is already saturated.
So it makes the model a more reliable calculator, but it doesn't teach it calculus. It's just wasted compute if the goal was capability extension.
Correct. Now, for the OD tasks, where the goal is capability extension, the situation changes. RL did improve pass at 128, so genuine capability gains, but only when applied to the OD edge data, the op equals 11 to 14 range. This is the critical finding. When they trained RL on data that was either too easy, so the ID stuff, or too hard, like op 17 to 20, the capability gains just vanished or were negligible.
Wait, why does trying to teach the model the absolute hardest problems fail, even with RL? Shouldn't RL be optimized to explore and find those solutions?
This is the concept of reward sparsity. If the O to hard task is so complex that the base model has near zero accuracy, the model virtually never generates a correct solution, not even in a sample of 128 rollouts. Since it never reaches the goal, it never receives a non-zero reward signal. RL relies on that signal to guide exploration. If the signal is absent, the model can't learn the compositional steps needed for deep extrapolation. It's blindly wandering in the dark.
It's like throwing a dart in a pitch-black room. Even if you get feedback eventually, the path to success is just too long, and the probability of hitting the bullseye by random chance is effectively zero.
That's takeaway 1, which the researchers dubbed the rule of headroom. True, measurable capability gains only happen when 2 specific conditions are met. First, the task must not have been saturated during pre-training, leaving sufficient headroom for the model to explore and learn new, deeper compositional structures. Second, the RL data must be perfectly calibrated to the model's edge of competence.
That sweet spot.
Exactly. It must be difficult enough to necessitate novelty in composition, but not so challenging that the reward signal becomes too sparse to be useful. When they calibrated it correctly, they saw substantial gains, sometimes over 40% improvement in pass at 128.
A 42% lift is conditional on finding that sweet spot.
As a practitioner, how do I actually find that edge of competence in my own training pipeline? It sounds highly technical and specific. It leads to extremely tactical guidance for data curation. You shouldn't just dump all your hardest examples into the RL phase. Instead, you must use the model itself as a filter. The recommendation is to design your RL training data by filtering for tasks where the base model fails at pass at 1, but succeeds at a higher pass at K, like pass at 128.
That creates a perfect self-paced curriculum.
It does. You are selecting problems the model can solve, which means the primitives are present, but that it struggles to solve reliably on the first try. That means the compositional structure needs refinement. This focused data avoids wasting compute on mastered tasks and avoids the sparsity problem on tasks that are too far out of reach. It confirms that the effectiveness of RL is not absolute. It is a function of the prior knowledge foundation.
So we've moved past the idea of just brute forcing RL with massive amounts of data. It's about surgical data selection, targeting the moment right before the model falls off the cliff of capability.
Exactly. It's about optimizing for that exploration boundary. We've established that RL needs a sweet spot for complexity, but fundamentally, it can't build something from nothing. It needs a base foundation, a seed. This leads us to the second major finding. How much exposure in the pre-training phase is needed to unlock contextual generalization?
Right, this is the question of transferability. Can a model learn the rules of arithmetic using narratives about space exploration and then immediately apply those rules to, say, a balance sheet template?
To test this, the researchers created a really elegant setup involving two reasoning contexts. Context A was the frequent context. It appeared often during pre-training and covered the full difficulty range from op equals 2 up to op equals 20. Context B was the long-tailed, sparse context. In pre-training, context B was strictly limited to only the simplest atomic operations, just op equals 2. It received the bare minimum linguistic or semantic seed.
So context B contained the language and the simplest possible logic, but none of the hard compositional structures.
Precisely. They varied the ratio of context B data in pre-training dramatically. 0%, 0.1%, 1%, and 10%. After this foundational pre-training, they applied RL using a balanced mix, 50% A, 50% B, targeting the full difficulty spectrum up to op equals 20. The RL phase was designed to force the transfer of the complex composition skills learned in context A over to context B.
And what happened when the base model was deprived of that initial seed?
Well, observation 2 revealed a clear failure threshold. When pre-training had 0% or 0.1% exposure to context B, RL completely failed to transfer complex skills to that context. The pass at 128 scores for op equals 20 problems in context B remained flat near zero, identical to the base model's failure rate. Contextual generalization simply fails because the necessary primitives, the linguistic seeds, the basic domain knowledge are missing.
That sounds reasonable. If the model never saw the language or domain rules associated with context B, RL has nothing to amplify. But 0.1% is still some exposure. Why did even that minimal amount fail?
Because the model likely treats that 0.1% as noise, a statistical anomaly that it just discards or fails to generalize from. It hasn't reached the density threshold required for the model to register it as a foundational primitive worth storing. Near zero exposure might as well be zero.
Okay, so what was the success threshold? What minimal density of data was needed to unlock the capability?
Here is the truly astonishing finding. Introducing just 1% density of context B data, and remember, only the simplest op equals 2 atomic examples during pre-training provided a sufficient seed. With this 1% sparse coverage, RL robustly reinforced the skills, yielding powerful cross-context generalization. They saw massive improvements, up to a plus 60% increase in pass at 128 for the hardest op equals 20 context B tasks, compared to the models trained without that 1% seed.
Wait, I'm still struggling with the idea that just 1% of the simplest examples is enough. Doesn't that sound counterintuitive to the established bigger data is better philosophy that has driven LLM development?
It redefines what kind of data should be big. This is takeaway 2. RL incentivizes contextual generalization only when the base model already contains the necessary primitives. You don't need massive data for complex examples in every domain. You need broad coverage of the basic primitives. The 1% seed is sufficient to establish the mapping between the new context language and the existing core arithmetic skills. RL then acts as the force that efficiently connects and composes those simple rules into complex structures.
So if you were building an LLM specialized for, say, patent law, a highly specific, jargon-heavy domain, you wouldn't need to feed it 50 million complex full-length patents during pre-training. You'd prioritize making sure your base corpus has 1% exposure to the basic legal terms, dependencies, and citation structures, and then let RL handle the complex synthesis later on.
Exactly. The practical guidance is to shift resources away from collecting vast quantities of highly complex, specialized pre-training data and instead focus on ensuring broad, sparse coverage of the basic domain language and rules. Get the atomic components into the model's lexicon, that 1% density, and trust RL to scale the complexity efficiently, utilizing that rule of headroom we just discussed.
This research also touched on whether LLMs are truly creating novel structures or just replicating patterns. In the context B scenario, were models with the 1% seed just replicating the logic they saw in context A.
That analysis was fascinating. They looked at the topology of the generated reasoning graphs. For the simpler problems, up 2 to 10, the models largely replicated the context A patterns, mapping that logic directly onto the context B narrative. It was mostly substitution.
But once the complexity increased,
As task complexity increased, so up 11 to 20, the models that had received the sufficient seed, the 1% and 10% B, started generating more novel compositional structures. These were graphs that didn't perfectly match any single context A example. This confirms that RL isn't just a replicator, it acts as a creative compositor, but that creativity is strictly conditioned on the presence of those foundational seeds established during pre-training. If the foundation is too weak, the creative leap is impossible.
we've detailed the foundation, so pre-training, and the accelerator, RL. But we need to talk about that intermediate step that is so often overlooked in public discussions of AI training, mid-training. This phase is crucial to modern success, acting as a critical bridge.
Mid-training, often using high-quality instruction data, is designed to align the model's broad, chaotic knowledge base from pre-training towards structured output and instruction following. It makes the subsequent RL phase more stable and effective.
Given that training costs are astronomical, the strategic question for any team is, if I have a fixed budget for post-pre-training optimization, how should I split that compute between mid-training, the supervised fine-tuning, and RL, the exploration? Do I do a little of both, or should I go all in on one? That was the precise focus of this section.
Yeah.
Analyzing the synergy under a fixed compute budget. They meticulously normalize the costs, ensuring that the total tokens processed for mid-training plus the approximate cost of RL rollouts equaled a fixed total budget. This ensures a fair comparison of resource allocation strategies.
What were the configurations that they compared?
They systematically varied the ratio of compute dedicated to RL, which they defined as beta. They compared full mid-training, so beta equals 0, full RL, where beta equals 1, and 3 mixing strategies, light RL, medium RL, and heavy RL. And they tested these mixes on both ODE-edge tasks and ODE-hard tasks.
Okay, so what did Observation 3 reveal about the optimal budget allocation? Does the answer depend on the complexity of the task? It absolutely depends on the task and your goal. If your priority is reliability on known structures, the OD-edge tasks configurations with light RL, where beta is 0.2, achieve the best pass-at-1 performance. Full mid-training was also very close to optimal. This tells us that mid-training is critical for instilling strong, stable, and highly confident priors, enabling the model to get the right answer on the first try. It establishes a strong baseline of competence.
So if I want my model to be highly reliable and precise on moderately difficult tasks like standard financial analysis, I should front-load my supervision with heavy mid-training.
That's the strategic choice for stability. However, the trend flips when you pivot to the most challenging objective, exploration and generalization to truly novel structures, the ODE-hard tasks. Here, reallocating the compute budget toward heavy RL, so beta is 0.8, substantially improved overall performance in both pass-at-1 and pass-at-128.
That makes perfect sense. To gain true capability on the hardest unseen problems, you need to dedicate the majority of your budget to the exploration and composition that RL provides, leveraging the small seed of structure provided by mid-training.
That is takeaway 3. Mid-training is an underexplored lever, and compute allocation must be task-aware. Mid-training instills the stability and high pass-at-1 reliability needed for edge structures, while heavy RL is the indispensable phase for achieving true, far-reaching capability extension on the hardest ODE structures. Crucially, the combination consistently outperformed RL alone by a significant margin, over 10% on ODE-hard tasks, confirming the powerful synergy.
Let's tie this back to real-world models. You mentioned Quinn and Llama earlier. How does this finding about mid-training explain the observed differences in performance we see in the ecosystem?
It helps us understand the concept of RL readiness. When researchers first started applying RL to various base models, some like the Quinn series seemed inherently more responsive and easier to align. Architectures that lacked a dedicated, focused mid-training phase, such as early versions of Llama, often struggled initially to achieve similar high-quality RL results.
Why would mid-training make a model more RL ready?
Mid-training acts as a critical distributional bridge. The massive pre-training distribution is broad and messy. The final RL task is extremely narrow and reward-oriented. Without mid-training, that jump is just too large. Mid-training, especially when focused on reasoning, reduces catastrophic forgetting and eases adaptation by aligning the model's internal representations. It teaches the model how to follow instructions and generate structured chain-of-thought outputs, which is exactly the format RL relies on.
So mid-training isn't adding massive new knowledge. It's installing the operating system necessary for RL to function efficiently. It's making the model disciplined.
Precisely. It instills the essential priors, the stable pass-at-one competence, that RL can then efficiently amplify through exploration. The models that were later subjected to structured mid-training, even Llama, subsequently achieved RL performance comparable to the stronger purpose-built bases. The practical lesson for developers is design mid-training to install stable priors and RL to scale exploration. That balance is the key to maximizing utility under a fixed budget.
We've established that RL is powerful but conditional.
Mhm.
However, we keep coming back to RL's Achilles heel, reward hacking. The model gets rewarded for the output, but the process is spurious or nonsensical. How do we prevent the model from cheating the reward function?
Reward hacking is not just an evaluation problem, it's an optimization bottleneck. When you use simple, sparse, outcome-based rewards, the model optimizes for the shortest, simplest path to a one signal, which often means finding statistical shortcuts rather than learning fakeful compositional logic.
And since the controlled framework already uses the process-verified evaluation to grade the results, the logical next step is to integrate that same fidelity requirement into the training reward itself.
Exactly. The question became, can process-aware supervision mitigate reward hacking during training while still preserving the generalization benefits of RL?
How did they manage to provide dense process-level feedback without massive computational overhead?
They augmented the traditional sparse outcome reward with a process verification reward. This provides a dense signal at every reasoning step, calculated based on the correctness of that specific intermediate calculation or dependency match.
So instead of model getting a 1 only at the very end of a 20-step process, it gets a small, dense reward signal, maybe 0.05, for every correct intermediate step, guiding it incrementally.
That density is key. They used a composite reward function where they could tune the balance between the final answer and the fidelity of the process. They also tested a very strict formulation, granting the full outcome reward only if the entire reasoning process was 100% verified.
What were the results when they implemented these process-aware rewards? Did it slow down generalization, or did it actually improve fidelity?
Observation 4 confirms fidelity gains. Integrating process verification consistently improved performance, resulting in a measurable 4 to 5% increase in pass-at-one accuracy on the toughest extrapolative settings. The strict reward formulation, where you only reward the final outcome if the process is perfect, yielded the most substantial gains. This confirms that guiding the process, not just the outcome, is crucial for improving reliability and capability on complex, unseen tasks.
So by forcing the model to be honest about its steps, you actually increase its overall capacity to solve hard problems. That's a powerful lesson.
It is. The detailed analysis of error types, which they showed in Figure 8 of their paper, clearly demonstrated why this works. When they compared models trained with only outcome reward versus those trained with a significant process component, the models with process supervision saw a dramatic reduction in structural errors.
What are structural errors in this context?
Structural errors are things like dependency mismatch, using the output of step 5 before step 4 is complete, or missing nodes, where the model skips a critical intermediate calculation. Outcome-only rewards let the model exploit shortcuts that cause these structural flaws. By rewarding process verification, the model is trained to generate faithful reasoning behavior, reducing those foundational structural flaws and leading to more reliable generalization when tackling truly novel compositions.
So takeaway 4 is clear. Process-aware rewards are not a luxury. They're essential for scaling genuine reasoning.
Absolutely. The blend of sparse final outcome signals and rich, dense process-level feedback is the path forward for RL-based generalization. If you want faithful, shortcut-free reasoning, you must enforce the steps, not just the answer. This is especially true as you move into the ode-hard territory where the model is exploring true novelty.
So what does this extraordinary, highly controlled deep dive tell us? It moves us past the simplistic, decades-long argument about whether RL works or not. It reveals that the effectiveness of RL is not a given. It is entirely conditional on the foundational work done in the prior two stages. The synergy is everything.
That is the perfect summary. For anyone building, evaluating, or deploying advanced reasoning LMs, this work provides 4 core, actionable insights that move us from brute force experimentation to strategic surgical training pipeline design.
Let's synthesize these 4 major takeaways one last time, framing them as developers' checklist.
First, RL is an amplifier, not a primary creator. You must target your RL efforts surgically. Use RL data calibrated to the model's edge of competence, where pass at 1 fails, but pass at 128 still shows non-zero capability. That is the sweet spot for maximizing capability gains and avoiding reward sparsity.
Second, pre-training is the domain knowledge scaffold. To unlock contextual generalization applying logic across new jargon, you must ensure broad coverage of basic domain primitives. A surprisingly small amount, around 1% density of simple examples, is the required seed to allow RL to compose complex reasoning later.
Third, mid-training defines RL readiness. Compute allocation is strategic. If your goal is stability and high pass-at-one reliability on known structures, allocate the majority of your budget to mid-training. If your goal is maximizing exploration and capability extension on truly novel, hard tasks, allocate the majority to heavy RL. But always ensure mid-training establishes the structure first.
And finally, fourth, fidelity demands process verification. To combat reward hacking and ensure faithful compositional reasoning, you must integrate dense step-level process verification into your reward function. Rewarding the steps, not just the outcome, is the only way to scale reliable performance.
And if we look at the broader implications for the AI field, this research firmly grounds capability development in the idea of a comprehensive training curriculum. The performance ceiling of your final aligned model is predetermined by the decisions made in pre-training and mid-training. We can no longer treat these stages as isolated sequential steps. Their interplay is the source of the most significant, generalizable, and verifiable gains.
It changes the conversation from let's throw more data at it to let's design a smarter training recipe. Future research and the future success of commercial models will depend entirely on mastering this strategic interstage optimization. That's it for this week's deep dive. We hope this gave you the shortcut you needed to be well-informed on the latest in language model reasoning. Thanks for tuning in, disclaimer. This video podcast is generated with Google's Notebook LM by Vin Genian at VinHanks based on research.